we have everything in three-dimensional space now. We have a hook that a 90-pound force is pulling it down. Now, this hook obviously is attached to a rope or some kind of connection. It seems to be a rope. And while it's being pulled down, it's being held by three forces. One force is coming from a rope AD holding it, and that rope is connected at point D to some support or wall. Another force is coming from cable CA. Right? That CA also is connected to a wall at point C. And the third force is the spring attached to this point, right? Point A, which all the forces and the hook is connected to. In one side, and the other side is attached to the wall. Now, we know the value of the force pulling the hook, and we know the stiffness of the spring. So what are we looking for? The problem is telling us that a 90-pound load, obviously, is suspended from the hook. We don't really see the load here. We just see the force vector. Now, if the load is suspended by two cables and the spring, with the stiffness, all the stiffness is given on the figure, with the stiffness K, with the stiffness K is 500 pound over foot, right? Pound per feet, it's the unit for stiffness, if you remember, which is force over distance or length. We are asked to find the force, in cables and the stretch I guess we can just say on the stretch of the spring for equilibrium. It says equilibrium. Right, everything is in equilibrium position, obviously. Now, what we know is cables. We already know that, but just add it to make it a little easier when we're looking at this three-dimensional figure. Cables, or better to say cable, I'll talk about them separately. Cable AD, which is this cable here, lies in the XY plane. So it is in XY plane. And cable, this cable AC, cable AC lies in XZ plane. Right? XZ plane. Just so you know, guys, in this course, I try to always write the whole problem statement. And the reason I do this, because I came to this realization that a lot of time the problem is, or could be when you're solving a problem, is that you actually don't read the problem statement properly and you don't get the information from the problem statement. A lot of time, if you actually read the problem statement or example properly and carefully, you pretty much get the answer to a lot of questions you have in mind about the problem. So I found it useful to have the whole problem statement in front of you when you're trying to solve a problem. Don't just jump into what you know and try to use that. Try to read the problem and think about it a little bit, what we are asked for. So in this case, we are asked to find, let me change this, to find the force in cable AD and AC. Well, the most obvious approach is to, let's draw a free body diagram for point A, because that's where everything is connected. And as a rule of thumb, when you want to draw a free body diagram, in this case, there's only one possibility. But if you have multiple things connected and you want to draw the free body diagram, as a rule of thumb, not always true, but works in so many cases, start with wherever you have the most information. Try to incorporate that information into what you want to do at first. So here I know I have information about the force pulling that hook is 90 pounds. Well, I'm going to draw a free body diagram for point A because that includes in that free body diagram, and I'm using the information I'm given. So if I draw that, let me try to actually draw the, or maybe draw the axes here to make sure things are more clear. Let's say this is my X axis. This is what is my Y axis, and this is Z axis. Has to be a little this way. So I'm just going to name them. This is X, this is Y, and this is Z. I'm going to draw my vectors on top of these. Now, if this is point A, you guys tell me what forces do I have here on this free body diagram. All right, let's say this is my free body diagram, and this is point A. My axes are passing through point A. What forces should I draw here?
You have the spring force going to the right of Y.
Yes, Joshua, thank you. You have the spring force here. All right, let me see if I can use, why not? Use black. So this is the spring force this direction, and let's call it, I can call it Fs, but let's call it FAB. So it tells me about the direction in which it's applied. What else?
You have cable AC in the XZ plane.
I have cable AC, as Elizabeth said. Right, we go this way. Right, try to put it in this. I'm just going to call it TAC, and it is in that plane. So if you want to think about, let me do it this way. Maybe that helps. So it is in this plane.
Did the display cut out?
You guys cannot see my screen.
I don't know if it's just on my end.
Can I get feedback from others?
It might be you.
I can see it.
I see it. I can see your screen.
I see.
Okay.
Okay, so I don't know who was that with the problem, but let me know if it still exists. Or you can also log in and log out and log in. Might help. Computer science way of doing things, like reset it. Okay, so TAC is in plane XZ plane. What else? I have another cable, right? Obviously AD, so that is also a tension force there. I'll call it TAC or TAD, sorry, AC was the other one. And just to make it a little more clear, I'm gonna say these are, it's in XY plane. What is missing? Is everything there already, or we still need to put something else?
The force of weight.
The force from the hook, right? Exactly. So this would be 90 pounds. Now, here's a little bit of geometry, right? This part, right? We can write the equilibrium and say, well, in every direction, in X direction should be 0, in Y direction, the summation of forces should be 0, the same story in Z direction. Now, what are the components in X direction? I have to find that out. X is this axis. Right, this is X. So what do I have in this direction? A couple of things, pay attention. I'm given this angle. This is 30 degrees. How, is there any other angle that I'm given?
You have the complementary angle. It should be 90 degrees or 60
This
degrees.
one, you mean?
Yeah.
We can get that also 60 degrees. What else? Because the whole thing is 90, correct? If you look at the problem statement and the figure there, is there any information about a different angle?
The angle AC makes to the x-axis.
Yes, Richard, exactly. So this angle, right?
Yeah.
And that is given by, you remember we talked about this triangle, the ratio between sides. So this angle, if I call it, I don't want to use alpha, just call it theta. What is that angle? That angle is tan inverse in this triangle here, is the opposite over adjacent. Keep in mind 3, 4, 5 are not dimensions, they are ratios, because all we care about when we want to find an angle using trigonometry is the ratios between sides in a right triangle, and that is given. Dimensions can be anything as long as the ratio is that. So from there you can actually find theta. If you do the math, you will get 36.87 degrees. So now I have this angle too. And this is 36.87 degrees. Now let's see if we can write the components in X direction. So in X direction, what do I have? Now that you know these angles, you have enough information to write the forces along X axis. So TAC, right? I can find the X component here. Let me see if I can use a different colors. So this is the X component for TAC. That's one thing I have. So that would be TAC cosine 36.87 degrees. I told you before, get very comfortable with finding different sides of different sides in a triangle, in a right triangle, knowing different angles and hypotenuse or adjacent or opposite. Just get comfortable with that. Now, that's the magnitude of that. What is the direction of TAC in X along X-axis? Is it positive or negative?
Negative.
It's negative, right? Because it's on the negative side of X. It's pointing that direction. So I'll put a negative here. What other component along X-axis do I have from this free body diagram?
You have TAD, but only like times cosine to 60 degrees.
Exactly. So that would be plus TAD, right? Cosine 60 degrees. And I put it positive plus because it is in this direction, right? It's in positive direction. This is the X component. You could also write TAD sine 30 degrees, depending on which triangle you're looking at. Anything else in X direction? No, it's pretty much it. So 0. Okay, so Y direction next. What do I have in Y direction? I have FAB, right here. So FAB, no need to find components because it's already in Y direction. What else? Is there anything else?
Minus cosine or TAD cosine 30.
TAD cosine 30, exactly. Cosine 30 or sine 60, whichever you go. And it's negative because it is in negative direction, right? Let me see. I don't know, using different colors makes it more confusing or less, but this is going to be the direction. So it's negative. It's towards negative y. And so minus TAD is equal to 0. Now look at the z direction. That's pretty much it. Whatever, everything I had in y, along y axis. How about z direction? What do I have in z direction? Well, obviously I have 90 pounds there, and it's downward. Sorry, Connor, I just saw your text on chat box. But yes, pretty much. Well, cosine 30, but it could be cosine, it could be sine 60, depending on how you look at that triangle. So in z direction, I have minus 90. What else? What other force has a component along z direction?
TAC sine 36.87.
Thank you, Richard. Yes, TAC sine 36.87 degrees, and it's positive because it's upward. Right? Don't get lost, folks. We are talking about this component here along z. That's pretty much it. That's all I have in z-axis. So what do we have here? We have 3 equations, and we have 3 unknowns. We don't know what is TAC, we don't know what is TAD, and we don't know what is FAB. So we should be able to solve this. 3 equations, 3 unknowns. Mathematically speaking, we have enough information to find these 3 unknowns. So my suggestion to you here, you will see it's pretty easy because I can start from this equation here, this one, and I find TAC. Once I know TAC, I can plug TAC back in this equation here and find TAC. Obviously, I don't know TAD yet. TAC, plug it here, and then the only unknown would be TAD in this equation. So I can find TAD. Once I know TAD, I'll come to the equation in the middle, this equation, and find FAB. So it works pretty smoothly. Now, sometimes it's not that easy. Sometimes you have 3 equations, 3 unknowns that they have to be solved simultaneously. My suggestion to you guys, any type of calculator you have, get comfortable with your calculators, right? Have a relatively good calculator, right? I have the, I think you can always look up the type of calculators you can use for FE exam. So that's my suggestion. This is the best one that I could have for my FE exam back then. So I still have it, right? I'm not advertising for anything. You can always look up the calculators allowed on FE exam and get a relatively good one if you don't have a calculator. If you have it, if you have a calculator that's capable of doing engineering calculations, you know, a little bit of advance, get comfortable with how to use with its capabilities. They all have capabilities to solve equations, you know, set of equations. 2 equations, 2 unknowns, 3 equations, 3 unknowns. Typically they have that. So get used to or get familiar with how can you use that calculator to solve 2 equations, 2 unknowns, 3 equations, 3 unknowns. Just spend a little bit of time on that. Solve some 3 equations, 3 unknowns, 2 equations, 2 unknowns with your calculators. It goes a long way. You are going to use that here, next course, later on in engineering courses. So my suggestion is just get comfortable with that. Sometimes it's easy, like here, you go from one equation to another, you can solve everything. Sometimes it's not that straightforward. So if we do the process I just said, like find TAC, then plug it back to the first equation, find TAD and FAB, we can actually find everything we need. So TAC becomes 150 pounds. TAD becomes 240 pounds. And then eventually FAB, I believe, will be 207.8 pounds. So this is what we were looking for in the first part of the problem. I'm going to come back to this page. right? It says find the force in cables. So we found the force in cables, TAC and TAD. And it is asking to find the stretch of the spring for equilibrium. Right? Now we found the force FAB, which is applied to the spring. Remember, for a spring, we had F is equal to KS. Right? Force in the spring is equal to the spring stiffness multiplied by the amount the spring is stretched or compressed. So I'm just going to use that property. So for the spring now, easily we'll say FAB is equal to KS. And from there, you can find S. S would be FAB over K. You already know FAB was 207.8 divided by the stiffness of the spring, which I'm given in the problem statement is 500 pounds per feet. So 500. And if you do this calculation, you'll get S, amount the spring is stretched. And this is going to be in feet. And there goes the second part of the problem. So these two are for the first parts of the problem. First part of the problem, that was the forces in cables. And here's this stretch in the spring.